These three objectives will be covered in two parts. At the end of this Part 1 video, you should be starting to be able to describe motion in terms of changing velocity, compare graphical representations of accelerated and non-accelerated motions, and apply kinematic equations to calculate distance, time, or velocity under conditions of constant acceleration. Chapter 2, Section 2, Acceleration. Changes in velocity. Many bullet trains have a top speed of about 300 kilometers per hour. Because a train stops to load and unload passengers, it does not always travel at top speed. For some of the time that the train is in motion, its velocity is either increasing or decreasing. It loses speed as it slows down to stop and gains speed as it pulls away and heads for the next station. Acceleration is the rate of change of velocity with respect to time. When a shuttle bus approaches a stop, the driver begins to apply the brakes to slow down about 5 seconds before actually reaching the stop. The speed changes from 9 meters per second to 0 meters per second over a time interval of 5 seconds. Sometimes, however, the shuttle stops much more quickly. For example, if the driver slams on the brakes to avoid hitting a dog, the bus slows from 9 meters per second to 0 meters per second in just 1.5 seconds. Clearly, these two stops are different, even though the shuttle's velocity changes by the same amount in both cases. What is different in these two examples is the time interval during which the change in the velocity occurs. As you can imagine, this difference has a great effect on the motion of the bus, as well as on the comfort and safety of the passengers. A sudden change in velocity feels very different from a slow, gradual change. The rate of change of velocity is called acceleration. The magnitude of the average acceleration is calculated by dividing the total change in an object's velocity by the time interval in which the change occurs. We see that average acceleration is equal to change in velocity divided by time required for change on the screen now. Acceleration has dimensions of length divided by time squared. The units of acceleration in SI are meters per second, which is written as meters per second squared, as is shown on the screen. When measured in these units, acceleration describes how much of the velocity changes in each second.
An object changing speed is accelerating. The equation for acceleration is the change in velocity divided by the time required for the change. Acceleration can be calculated by knowing the initial and final velocities and the initial and final times. Like velocity, acceleration must also include direction. The velocity of this cyclist is increasing by 1 meter per second south each second. His acceleration is expressed as 1 meter per second squared south. If an object slows down and is traveling in a positive direction, the change in velocity is a negative value, so its acceleration will also be a negative value. If an object has a negative velocity, such as when the bicyclist heads the opposite direction and is accelerating in that direction, the acceleration will also be negative, even though the bicycle is speeding up. If there is no change in an object's velocity, its velocity is constant and its acceleration is zero. If an object has constant speed but changes direction, then its velocity is changing and it is accelerating.
Acceleration has direction and magnitude. Figure 2.1 shows a high-speed train leaving a station. Imagine that the train is moving to the right so that the displacement and the velocity are positive. The velocity increases in magnitude as the train picks up speed. Therefore, the final velocity will be greater than the initial velocity, and delta V will be positive. When delta v is positive, the acceleration is positive. On long trips with no stops, the train may travel for a while at a constant velocity. In this situation, because the velocity is not changing, delta v is equal to 0 meters per second. When the velocity is constant, the acceleration is equal to 0. Imagine that the train, still traveling in the positive direction, slows down as it approaches the next station. In this case, the velocity is still positive, but the initial velocity is larger than the final velocity. So, delta v will be negative. When delta v is negative, the acceleration is negative. The slope and shape of the graph describe an object's motion. As with all motion graphs, the slope and shape of the velocity time graph, as shown in figure 2.2 on the screen now, allow a detailed analysis of the train's motion over time. When the train leaves the station, its speed is increasing over time. The line on the graph plotting this motion slopes up and to the right, as at point A on the graph. When the train moves with a constant velocity, the line on the graph continues to the right, but it is horizontal, with a slope equal to 0. This indicates that the train's velocity is constant, as at point B on the graph. Finally, as the train approaches the station, its velocity decreases over time. The graph segment representing this motion slopes down to the right, as at point C on the graph. This downward slope indicates that the velocity is decreasing over time. Acceleration can be positive or negative. A negative value for the acceleration does not always indicate a decrease in speed. For example, if the train were moving in the negative direction, the acceleration would be negative when the train gained speed to leave the station and positive when the train lost speed to enter a station.
Acceleration measures the rate of change in velocity. You can find the average acceleration of an object if you measure its velocity at 2 moments in time and divide the change in velocity by the time required to make the change. You can also determine the acceleration of an object from a velocity versus time graph of its motion. Consider an object whose motion is represented by this graph. Let's find the average acceleration for the time interval from 4 seconds to 10 seconds. Average acceleration is simply the change in velocity divided by the time of travel. In other words, the average acceleration equals the slope of a velocity versus time graph over a time interval. The acceleration at any moment, called the instantaneous acceleration, can be found by shrinking the time interval. As the time interval becomes infinitesimal in size, the value of the average acceleration approaches the instantaneous acceleration. The instantaneous acceleration at a particular moment in time is the slope of a line tangent to the velocity time graph at that time.
Figure 2.3 on the screen now shows how the signs of the velocity and acceleration can be combined to give a description of an object's motion. From this table, you can see that a negative acceleration can describe an object that is speeding up when the velocity is negative, or an object that is slowing down when the velocity is positive. Use this table to check your answers to problems involving acceleration. For example, in figure 2.2 on the screen now, the initial velocity, v sub I, of the train is positive. At point A on the graph, the train's velocity is still increasing, so its acceleration is positive as well. The first entry in figure 2.3 shows that in this situation, the train is speeding up. At point C, the velocity is still positive, but it is decreasing, so the train's acceleration is negative. Figure 2.3 tells you that in this case, the train is slowing down. Decreases in speed are sometimes called decelerations. Despite the sound of the name, decelerations are really a special case of acceleration in which the magnitude of the velocity, and thus the speed, decreases with time.